Lina, good. So recording in progress. So we are happy to have Andrei Grekov from Stony Brook, and he will speak about the topic with title is on his first page, moduli spaces of instantons and integrable systems. Andrei, please.
Yes, thank you, Jan, and thank you very much for inviting me here. Yeah, I'm really glad to finally give some talk in many years. Yeah. So okay. So this is the talk based on my joint work with Nikita Nekrasov. As you probably might know, he was working on this topic already for many years. So in the beginning, like I will have to introduce first of all the problem which is still not solved there, because a lot of it was already solved by him, and also I'll have to introduce his methods, because he went very deep into this subject, and maybe many people didn't quite catch up with what he was doing there. So it'll be a lot of introduction first. So the plan. At first, review of integrable systems, plus what is separation of variables, then Nikita's methods, review of Nikita's methods briefly. So the moduli space of instantons, and then I will state the main result. Yeah, the fourth point was like applications of the main formula. But I don't know whether you'll have time to get to it. Okay, so let me start. First of all, what is an integrable system? The classical integrable system. Part one. So the classical integrable system is a phase space, which is symplectic manifold, say of dimension 2n, and a set of n functionally independent Poisson commuting functions on it. In principle, I think that's all. The question is which integrable system you like to study. It's more like there is some set of nice examples which people work with. For example,
And Andrei, you do not assume that your symplectic manifold is compact.
Yeah, not necessarily. No, why? Usually, like for the simplest integral system is usually like R to n, like the in if it's like a system of particles, or I don't know, or something like that. Very simple systems, like say particle in line, it will be already T star of R, right? So.
And your symplectic manifold will be real symplectic manifold, not complex.
Well, it's actually a good question. So for physical, for physical purposes, yes, but what we will obtain from gauge theories will automatically be complex, and then you could choose a real form, the real slice, if you want. So yeah, in principle, it could be complex as well. Yeah, don't. So for our purpose, it will be needed. Yeah. So, for example, the simplest case, but still relevant to our talk, is say the Hamiltonian of Calogero-Moser system. Square. So here, these variables pi and qi are canonically conjugate to one another under the standard symplectic form. So the nice thing about
yeah, but now comes the question, because when you say, I mean, I'm a bit pedantic here, but when you say functions and
Yeah, I
when
know
you
how it
say,
shouldn't be singular, right?
yeah, they shouldn't be singular. Yeah, or at least you can remove diagonals from Rn before taking the cotangent bundle.
Yeah, that's fair. Yeah, I mean, technically, like, yeah, maybe, yeah, there is like a question what kind of potential we should allow. Yeah, so indeed, maybe I should have included some kind of broader definition to write down such Lagrangian, indeed, such Hamiltonian. Yeah. But yeah, I don't want to like focus on it too much. Yeah, the nice thing about this integrable systems is that frequently we have a lax pair representation for it, which means that if we have our dynamics qi and pi effectively recast into some dynamic of matrices. For some matrices L and M of some size, some rank. And this is kind of very general phenomena, and it might have various representation theoretic meanings. For example, one famous example is L is just it just came from the function of the on the duality algebra, and it's like which is naturally symplectic manifold. I'm not sure. So we could.
No, dual to
Sorry.
to the Lie algebra is not symplectic, it's
Yeah,
only Poisson.
it's Poisson. Yeah, but we could restrict to the orbit. Yeah. So that's yeah, you're right.
Yeah,
So
but this arrow which you write, you say, I mean, it looks like for the people who see it first time that having any Hamiltonian system, you can construct such L and M so that your Hamiltonian system is equivalent to something else, to some other differential operators in matrices. But probably it's not it's not true that any, or is it true that any Hamiltonian system has lax form?
yeah, I think no, because it automatically implies that we have conserved quantities, right? We'll have d over dt of trace L to the power k being 0. So this is like, this dynamic is isospectral. It preserves the spectrum of L. In other terms, preserve the determinant x minus L. Yeah, for example, for the Calogero-Moser system, the L looks approximately like this. It's n by n matrix. Yeah, in principle, I agree that it's like a big topic, and there should be like a whole talk about it, what L actually is, and how to obtain them. Yeah, there is a lot of techniques, basically, how to obtain integrable systems from, say, reduction and symplectic reduction and other tricks.
I understand, maybe I also know something about that, but the general question, because you do not have to assume that people in the audience know anything about integrable systems, except maybe of the very definition of Liouville integrability, which is your definition of the integrable system. So then the question is how this kind of notions are related to each other, whether having a matrix differential form in the Lax form, you can construct some Liouville integrable system and the other way around. So that's rather, or these two cover different classes of integrable systems which overlap.
Yeah, basically, if you have a Lax dynamics, you automatically have the traces of L to be some consort quantities. So yes, it's you're automatically having some integrable system.
But what commute with what is a
yes, you're right.
symplectic
Sorry.
manifold?
Yeah, you're right. They're not necessarily indeed. Yeah, in the weaker sense, basically. Here I only introduced one flaw. Indeed, if you want to have them all commuting, yes. So if you have multiple times, yes, for every Hamiltonian, each will have its own M matrix. Yes, and indeed, in order for them to be commutative, it usually requires some additional structure like classical R matrix, and this MK, they're all related. They're all obtained from this R matrix, indeed. So yes, the Poisson structure also usually should descend from some higher manifold but it has natural algebraic definition. Yeah. Well, maybe I should have said that too.
It's still not clear, but maybe let's move on because.
Well, let me just quickly, as a devil's advocate. So I can imagine that the H's are Hamiltonian and the P and the Q's are the functions. So the L is a vector field, and what is
no,
M?
No. L is not a vector field. L is a matrix-valued function of unknown at this time number of variables.
And what is the M here?
M is something. The point is that if you're given some M capital, you can write down a differential equation looking for another matrix L, which depends in the simplest case on time. You know, it's
commutators in the matrix form, right?
Yeah, and you can, and then indeed there is a kind of an easy computation due to Lax that the spectrum of L is preserved along this floor, and
so
that's
that
what.
L dot that.
But my question was how these strange matrix-valued differential equations are related to Hamiltonian integrable systems, which people might have seen in textbooks. And
that was exactly my question.
And so far, the answer was not given, but maybe let's move on.
No, in the Hamiltonians will be this, yeah, usually.
But what I mean this, as far as I can see, K, the number K can be arbitrary or what?
Yeah, but if the matrix is of size n, then the higher one will be dependent on the lower one. Yeah, but you're right that the size of the matrix, well, in simplest examples like for n particle Calogero is indeed of size n. Yeah, actually there exist other Lax matrices for Calogero which of bigger sizes. So no, yeah, it's not.
The problem is that when you can, of course, write hk equal 1 over k of trace of the power, which is good. But where is symplectic manifold on which hk are the functions, commuting functions? Where is the symplectic manifold?
Yeah, so that's basically, you mean how to obtain coordinates back from this matrix dynamics? Yeah, that's usually like a skill. For example, for this system, right, which I wrote down, you start from cotangent bundle to GLN, and then you which is symplectic manifold, and there you study the simple dynamic, trivial dynamic of matrices, which then you could symplectically reduce, and then you'll get this Hamiltonian. So basically, you have a moment map.
Let me try to repeat, and so maybe people. So you take the Lie algebra GLN, which is the same as duo at the Lie coalgebra. So T star is just a product of two copies of GLN, yeah?
Yeah.
And your HK will be functions on this cotangent bundle. Is it correct?
Well, yes. Basically, yeah. Okay. So indeed, everything will come from the symplectic reduction of this manifold under the group action. Both will obtain the Lax matrix and the Hamiltonians as well.
Yeah, and symplectic reduction means that you do not consider just T star of GLN, but you take the Hamiltonian action of the group GLN, which is a joint action on its Lie algebra, and lift it to the cotangent bundle, and then you do the symplectic reductions, which my students should know by heart. But so basically you look for the moment map to GLN, you take the pre-image of 0, and then you quotient by the action of GLN. It's symplectic. Of course, it can be singular, but probably you're not bothered with that. Okay.
More or less, yes. Yes.
Okay.
Yeah. Yeah. Sorry if I don't give enough motivation. Yeah, I wanted. It wasn't clear basically what kind of background people have, so I thought like I'll put a little bit of introduction in the beginning.
Yeah,
but not too much.
that's okay.
I mean, if you wanted me to give more, I should have done more. Yeah.
Maybe you assumed more than actually we know. All right, but anyway, so
yeah, because of course I should start that there's a huge theory here of how to obtain this Lax matrices and how and R matrices, and so to have natural Poisson structure and visual descent on the phase space of our actual integrable system.
Yeah. Okay.
Yeah. So. But now we actually.
I don't think you want to give a precise formula. Just want to see that the M is somehow determined by the symplectic manifold and Hamiltonian system, or that's just coming completely somewhere else.
Zhongzhu, my suggestion is to move on, because
that's
you know this
not to give a precise formula.
This R matrix approach to integrable systems. You saw there is a book by, I believe, Babylon and somebody else, which is like, I don't remember, 600 or 1,000 pages,
yes,
which is devoted to this too. So indeed, we can. I can give a 1 year course on it. So let's just move on, because it's not clear in this story what kind of geometry, where are instantons. So far, there are just two types of differential equations. One is standard Hamiltonian systems, and the other one, less known, it's this Lax integrable systems. All right.
Yeah, right. I actually was planning to give a little bit more, because we'll need Lax metric with spectral parameters.
Go ahead.
So that I don't know. In principle, the spectral parameter might appear if our initial Lie algebra was some sort of affine Lie algebra, and then we'll have evaluation parameter, and then we'll have some sort of L matrix depending on this parameter. But there might be other ways how it appears. So L might be function of additional parameter t. For example, the first non-trivial example, which is directly relevant to our talk, is elliptic Calogero-Moser system. Then the Lax matrix for it will look like this. Sorry. Yeah, compared to the previous case, xi just exponentiated coordinates, and theta q is the theta function. So, and E1 is its logarithmic derivative. Or maybe plus, yeah. So now the spectral determinant will become curve. Well, I mean, this equation, the equation of this equal to 0, will determine some sort of curve, which in this case is n-sheeted cover of the elliptic curve, where the parameter z lives. Sigma tau. Okay, so now, yeah, I have to probably motivate, give a little more motivation why this object is important. And here maybe I already myself don't know everything, but part of the conjecture. But as we see that the coefficients are still consort quantities. There was a conjecture. I don't know who was the first one to write it down, but I read about it in a paper by Sklyanin in 1995 called Separation of Variables, New Trends. The conjecture was that some special points, x, z, on the spectral curve, and they will serve as separate variables for our system. And specifically, the conjecture was that the poles of the Baker-Heisler function will be the needed variables. The Baker-Heisler function is related to is basically the eigenvector of this equation. So if we normalize it in a certain way, it will have the right amount of poles as a function on the elliptic, as a function of the spectral curve, and these poles and the eigenvalues which are dual to them will be the canonical variables. And of course, it's entirely not obvious why it should be true and why they should Poisson commute and so on. But in his paper, he gave some examples, basically showed some examples. And
in
true,
what generality this is it for particular for Calogero-Moser system, or it's for any lax integrable system which depends on the parameter or what? Yeah,
that's a great question. For me, like, I think first of all, for elliptic Calogero-Moser, I think this was proven by Krichver in his paper elliptic solutions to quantum differential equations and integrable many-body systems. I think he gave more or less the proof there, and Sklyanin gave a couple of more examples in his paper, which are like famous one, like I think spin chains maybe. But in general, yeah, I don't know. It's a great question. Maybe if you ask like bigger experts than me, say maybe Nikita, maybe he'll say that it's kind of obvious for him in some in some way, or I don't know. But for me, it's not really obvious. And why it should be like in what generality should hold, and as any counterexamples, basically I don't know how
Yeah,
to.
but let me ask you a kind of more basic equation. So you wrote this differential equation in Lux form, and your L was just I don't know, n by n matrix, n is fixed, depending on time. So it's a curve in the space of matrices. Next, you say that you consider more general. You allow L to be mathematically, probably should call it the loop space, because if you have one variable L of z, so it matrix depending on the parameter z in addition to this time t. So then it kind of it's infinite dimensional Lie algebra. It has it takes values in the infinite dimensional Lie algebra, something like GLN tensored with I don't know with what now, with analytic function and Z, with Laurent polynomials, with Laurent series. What
Yeah,
kind
yeah,
of
yeah. I guess some sort of Lorentz series. Well, I mean, in case of Calogero, for example, it has a pole, right? At z equals 1. And
But
so
basically, hold on. But basically, you look for the same type of differential equation, like L dot equal commutator of L with some M. Now everything will depend on this loop variable Z. Yeah, is it correct?
yeah, right. But actually, if you check everything, like if you write down this Lax equation, you in the Calogero variables, right? You
No,
write down L.
no, I am not. You see, Calogero, if I ask all people, in maybe most of the people in the audience, they know nothing about Calogero. And although I saw maybe Calogero many years ago, but again, it doesn't tell me anything. I should not pray seeing this, whatever Calogero-Moser system is. My question is if I have kind of in an abstract form this Lax equation, all right, so then either where L depends on an additional parameter, either something called spectral curve, like you wrote some abstract determinant x, some auxiliary variable minus L of z, because
Yeah, right. But it still will be. You mean with a determinant will be infinite dimensional or something? Yeah, probably in all examples. We use some sort of evaluation representation, and the determinant is understood as like finite dimensional.
but when your
But there are.
dependence L of z cannot be formal, it cannot be Laurent series because you cannot put then z equal to a particular number. It should be some algebraic or analytic, I don't know, meromorphic, but then it's not a formal thing. L of z is not just a formal loop. It's not an element of the piece of the affine Lie algebra. Right.
Yeah, that's right. In this example, for example, Calogero, it's not like this. Yeah, I mean, it's a
Yeah.
concrete
Okay.
function of z. Yeah.
All right.
I will talk about this affine Lie algebra, just maybe to some kind of motivate how like one way how some sort of additional z variable might appear. Just I feel like, yeah, I always feel like this little bit the z in the treatment of integrable systems, this spectral parameter kind of appears out of nowhere, right? Like we start talking about here we have a spectral curve if L depends on z, but it's like
In
for.
some sense, yes, but as you mentioned kind of briefly, that if there is no parameter, then one way to produce this type of equations is to look for the coadjoint orbit in the Lie algebra. So now if you take, instead of finite dimensional Lie algebra, you take a loop algebra with this finite dimensional, tensor it with something like Laurent polynomials or something, then you can kind of argue that there is a generalization, and at least it will be convincing. So you have a coadjoint orbit in some Lie algebra, which is infinite dimensional, which is a kind of like Lie algebra of the affine Kac-Moody, whatever. And then, but then the question is whether there is a canonical way to associate a curve, which you call the spectral curve, and for which probably what you wrote, I'm not sure, but probably this psi BA stands for Baker-Heezer, probably it's a section of some maybe line bundle on this curve or something like
Yeah,
that.
that's right. Mm-hmm.
Yeah, so then...
Yeah, maybe that was misleading because for Calogero, you're right. I think at least like in the simplest derivation for elliptic Calogero-Moser, parameter z doesn't appear as evaluation parameter in any representation. It appears from the fact that the symplectic reduction, which we're starting from, if we already start talking about it, for here, T star GLN. For elliptic Calogero-Moser, it becomes some sort of cotangent bundle to holomorphic to the space of holomorphic bundles on the Riemann curve, and then we need to symplectically reduce it, and that's where parameter z originates.
Okay. So then it's not trivial. Yeah. Okay.
Yeah.
Because
So
T star of band G, it's a modulo of Higgs bundles. It's more complicated. Okay. All right. Okay. Got it. Thank you.
yeah. Sorry, you're right. Basically, my talk is here is very confusing and messy because I'm trying to throw in motivations, having one examples in mind, and then we are applying it the same results in a completely different setup where some intuition coming from this motivation already doesn't hold. Yeah. So that's why how your question arises. Yeah. So yes, very good that you asked them. Yeah, so now the last step which we need here is that in this paper, Sklanin also gave some sort of quantum analog of this conjecture. Basically, also, yeah, there is also another big question: what is a quantum? Like, how do we define properly quantum integrable system? But in my case, we'll always talk about some basically very simple quantization of our integral system. We'll just replace pi with differential operator like this for Calogero, and we find some analog of some Hilbert space and some analog.
I hope that I is not equal to I.
Sorry, yeah, of course, yeah. Let's call it J. We have some sort of quantum Hamiltonians which act on some Hilbert space, and they commute, and they obtained from quantization of those classical ones which I introduced before.
That's nice, but what does it mean if your integrable system admits a presentation in the Lax form? What do you call quantization?
Yeah, for that, no, the Lax metric is not immediately quantized directly. There is such notion as quantum Lax pair. It in principle exists, but the quantum Hamiltonians are not just traces of powers of this Lax matrix in any form, and it's, well, I don't know, it's less popular, so to say. It's not, well, it's not really that common, and I think it's not even that well formalized. But we still hope that there is some sort of, well, instead we basically work with the quantization of a spectral curve equation itself, which is probably it's called usually some kind of TQ relation or something like that. So basically, we have this gamma getting replaced by some sort of differential operator like this. Of course, there's always the question of how the ordering, what ordering should be there, yeah, and that's probably relates to the question how to obtain this ordering naturally, and which is non-trivial, yeah. But in the main part of the talk, we'll obtain some natural ordering, basically from geometry we'll obtain it in the right form. That's will be the point. This quantization there arises naturally from geometry. Yeah, so and this differential operator might act on something, on some function which we call Q separated variables. And the hypothesis was that this Q serve as a wave function in separated variables. So basically, if we have a psi wave function written in coordinates x1, xn, the regional coordinates, that it will have the form of some sort of integral transform broadly of some kernel with some kernel of this product with these functions q sv. So that's like the hypothesis that the integral might be some sort of sum or some sort of transform. It's not very.
I have a question.
Yeah.
Suppose that you have an honest spectral curve, like gamma xz equal to 0, where x and z just complex variables, and suppose we even live in something like C star, which means x is a complex number and z is a complex. So first question is, do you have here a dx or h bar dx when you quantize?
Yeah, actually, because yeah, so it's related on it depends on the concrete Poisson structure on these variables, yeah, and as I said, it's non-trivial, yeah, and you're right. Actually, while you were speaking, I realized there was a little mistake here. Indeed, it should be for Calogero-Moser. Because of this, we did it in geometry. We found it inexplicitly, yeah, and so I just know the answer. Yeah, sorry, I forgot the eraser. It's actually just some sort of exponent hdx or something like that. It's like that. So they are conjugated like this for this particular example.
No, but it's not, no. What you are writing, you're saying that you have not a differential equation, but a difference equation. It's not a big deal. But my question was whether you have h bar in front of dx even in the differential case. So looking at your example of Calogero-Moser, where you have a shift not by 1, but by minus h bar, I assume that you do have this h bar d over dx in the differential case as well.
Yes, right. So
Yeah, and so this I understand. Now, if you have a differential or whatever difference operator, you can ask for its kernel, space of solutions. Of course, there is a question where in which class you look for those solutions with Q, whatever, of X. I don't know why do you put this separation of variables, because so far everything seems to be relatively invariant. What do you mean separation SV? Separation.
Yeah, just a notation, because the hypothesis by scanning that this QSV will be the wave function in separate variables. By this we mean that this formula holds that the wave function in original variables x1, xn will become some sort of integral transform of this form. So and that's formula is literally called.
So
this formula is called quantum separation variable, so to say.
Okay. So then it's indeed misleading. Let me explain for graduate students. So if you have a curve, probably you heard, or some of you heard, that there is a notion of quantum spectral curve. This is what Andrei is trying to say. Now, if you have the quantum spectral curve, it's a differential or difference or whatever, elliptic, it depends on the context. It's some operator. All right, so then you can look for solutions of equations gamma x, whatever, say he looks for minus exponent of minus h bar d over dx. If you look, this operator acts on the function. If you apply it to the function of x, it shifts it by minus h bar, just by Taylor formula for the exponent. All right, so it's a shift operator. And then you can look for solutions of the equation gamma, this operator, applied to some psi, which is called wave function, you see WV, equal to 0. So this is something which kind of every mathematician would do, but now the non-trivial claim is that there is another set of variables, which he called XISV, different from original variables x1 and so on, xn, and so that your wave function, this psi, is an integral transform of something else. And this something else also a solution of this, in this case, difference equation. So, all right. Okay, and where are the instantons in this story? Because, you can spend the rest of your life talking about integrable systems, but where is geometry?
Yeah, you're right. That's all. We're done with the introduction. So we try to move to basically geometry. Yeah. Okay. So basically part 2. But here I feel like you will definitely know everything better than me. Because
no, not everything. Don't be confused with that. Absolutely not. So.
Okay.
I cannot give review of Nikita's methods. I know maybe few of his papers.
So the manifold in question will be it's called MNK. One name is the Moduli space of instantons. UN instantons of charge K on R4 C2, which is given by IDHM clear description. It's called W. So V is a vector space of dimension K, and W is a vector space of dimension N. So this model space is a space of matrices B1, B2, Ij, satisfying the certain stability condition, which I could write down if you want. But it won't be really important for like the forms should be presented today, but yeah, plus stability condition. Quotient by the action of a group, GLV.
Well, and the main thing is subject to the equation, yeah.
Oh, sorry, of course. Yeah, there's also symbiotic reduction, of course. So yeah, indeed, we need to quotient by the group after we put the restrict to zero moment map, of course. Sorry, and subject to the equations. Yes. So that's right. And also the other definition, which will
just a
probably.
quick question.
Yeah,
you
sorry.
said this is the instance on Rn, that R later n.
On
Does that have
R4,
anything?
Zhongzhu, on R4, on four-dimensional.
Okay,
On
thank you.
four-dimensional.
That's
Yeah,
R4. Okay, thank you. That
Yeah, but
helps.
it's like you're right. N is just the rank of the gauge group.
Now I got it. Thank you. R4, C2.
Yeah, okay. So there's also another definition that it's equivalently could be understood as the moduli space of torsion-free sheaves on let's say on P2 rank n and C2 second Chern class equal to k with fixed trivialization infinity, which is called, I think, it's called framing. Yeah, so that's probably will be important for us only because we'll need a universal sheaf later. So yeah, and basically the main tool which Nikita uses all the time is equivariant localization. So for that we'll need a torus action, and the torus which we'll be using is the following. So Tn is a torus of GLN acting on this framing by changing trivialization, and this torus comes from the action on P2. So yeah, and the equivariant parameters for this torus will denote for in the K-theory case U1 and U1 U2. So I'll write it like this as exponents. It's big N. Yeah, so here I wanted to say something about it more. So the story holds in 3 setups actually, for equivariant cohomologies, equivariant K-theory, and something which is called equivariant elliptic cohomology, which is something I personally don't know very well. I don't know how it's defined mathematically, but because effectively we're working always with some localization techniques, which just produce some formulas over the fixed points. Formally, we could just always make them elliptic, and everything works. Yeah, but mathematically, I don't know how to properly define it very well. So I will always write, think, formulas for covariant K-theory, and then you, when you get the final result, right, some kind of formula, concrete formula, we could always obtain the answer for cohomology just by taking limit beta goes to 0 in the formula. So this will correspond to the elliptic Calogero-Moser system, which I talked about in the introduction. If we take beta, if we don't take beta to 0, if it remains generic, then we'll get elliptic Ruijsennars-Schneider system, which is a generalization of Calogero-Moser. And if we consider this mysterious elliptic homology case, then we'll get what's called double elliptic system, or something which is kind of related to it, which is not very well understood yet. I'll probably only briefly mention it, like in the end, like what these results mean for the system. Yeah, so I'll write everything for K-theory. So let's denote by K-theory localized covariant K-theory of this disjoint union, so to say. And now we could define a correlation function. So for any, say, class F in this KT, we just write by definition correlation function to be such kind of ratio. Yeah, well, I need to introduce notation. So Q is fugacity parameter, which measures the charge of instantons. Yeah, this lambda, it's just a weighted sum of exterior powers. No, it's natural definition. And T is the equivariant Euler characteristic. Yeah, so now people probably might ask, why do we have this cotangent bundle here additionally, how it's motivated? So the motivation comes from, at least for Nikita, yeah, from gauge theory, where this correlation function arises as an actual correlation function in this supersymmetric gauge theory, and this M is a parameter of hypermultiplet in the adjoint representation of the gauge group. So basically, this M will be related to the coupling constant of the Calogero-Moser system. If we just take M to infinity, we get rid of it. Instead of Calogero, we'll just get the total system. So the formulas without cotangent bundle, they also would make sense, but we want to work in full generality with Calogero because Calogero is more difficult, more non-trivial system.
You see this fugacity or whatever you term use for equivariant parameters, at least for me, the mathematician, it doesn't say a lot. But if you move kind of your F, first of all, is an element of the equivariant K theory, which probably you understand as equivariant sheaf, coherent sheaf. Otherwise, you cannot tensor it with anything.
Yeah, right. Sorry, I mean, you're saying basically what, that not every class has to be some sheaf, or is that you mean in full generality, so to say?
Yeah, well, in formal sense, you can speak about virtual sheaves, so you can do some linear algebra, but let's pretend that F is an actual equivariant sheaf. And so then you define this very strange generating function where, of course, it's probably impossible to understand why, unless there is some mathematical explanation, either or there is no mathematical explanation for this formula.
For motivation, yeah?
Yeah.
Yeah, so yeah, that I don't know, because it arises.
Is that some sort of a Kurzweil character formula?
No, it's more difficult, right? Because you mean Kurzweil for what? For
representations of affine Kac-Moody algebras.
Yeah, no, it's more difficult.
Who has the weights?
Yeah. I don't think in general it would be related to just Kurzweil formula. Yeah, it's
Nakajima quiver variety case. That's if you take you interpret things.
But maybe there is a different question. Either any representation theoretical explanation for this formula.
Okay.
Not necessarily whatever Katz formula or whatever it is. Is there any representation theoretical or there is none?
Yeah, let me think. So basically, the equivariant K theory of model space of instantons is the representation of quantum toroidal algebra. So it might have some sort of meaning like this. Yeah, but I think it only, well, as far as I remember, it worked in some limit, or there are some kind of maybe Pest and Kimura paper about it, that how to write this partition functions using these operators. Basically, well, okay, so there's another way as well. So indeed, there is what's called intertwiners in this quantum toroidal algebra, and the partition function could be obtained as some as a vacuum excitation values of this intertwiners in quantum toroidal algebra, or in this case it will be in trace. It's this is another story relating to representation theory. It's by wait, let me remember these names. It's the paper is called Quantum Algebraic Approach to Refine Topological Vertex, by Boris Fagin, Avata, probably I think Shreishi, Fagin, Avata, Shreishi, but it comes from the relation of the story to topological strings and solution of the topological strings in terms of refined topological vertex. So the causal relation to representation theory. Yep,
Yeah,
probably connect.
probably we should.
Yeah.
You see, there are too many unknown words, and the number exponentially grows, so that it doesn't make things easy to understand. Because even if you look for the denominator of this formula, certainly if f is a trivial sheaf, so you get one.
Yeah, just because I normalized partition, normalized everything by partition
yeah,
function.
but it's what you say, that you normalize, but you divide on the already non-trivial expression. What's the meaning of this expression? Is it some equivariant volume or what?
Yes, basically yes. In for the element in bit equals to 0, it will be I'm not sure. It's for non-zero m. It's more like not a volume. It's an integral of a Chern class of this cotangent bundle over this moduli space. If I didn't have M, indeed, and have considered just Toda case, indeed it will be just like kind of equivariant volume of this moduli space of instantons for Toda. Yes, that's what Nikita was originally calculating.
Okay, this
Basically,
what
yes.
mathematician knows Nekrasov. Okay, okay. All right.
Yeah, but it doesn't answer your question about representation theory here.
Well, it's I asked because Zhongzhu asked. He asked whether it's it's Katz character formula. It's not, but there might be some other more sophisticated algebras, and so this equivariant K theory or equivariant cohomology, which is simpler. It can be the space of representations, indeed, as he mentioned, like Nakajima's formula, the very first his formula where he explained this Goethe result for Hilbert schemes, which rank 1 instantons. Yeah, you have cohomology, not the K theory, cohomology of the moduli space of rank 1 instantons, and the Heisenberg algebra, infinite Heisenberg algebra, acts there, and so you can deduce many nice corollaries of that. Yeah, so that's as far as I understand, that's what he asked for a similar story.
Yes, basically what I said is there is like a continuation of this Nakajima story, is that the whole, not just the Heisenberg, the whole quantum toroidal acts in its Fock representation, as in its Fock representation in the covariant K theory of the moduli space of instantons. Basically, it originally was for Hilbert scheme of points, which is like U1 case, but for N, it's like N tons the product of N Fock spaces. Yeah, and this quantum toroidal algebra acts there, including the Heisenberg subalgebra.
But you say quantum, but for Nakajima's story there was nothing quantum. It's just infinite Heisenberg algebra. Then, if you work still with cohomology of the instantons of the higher rank, it will be probably some Kac-Moody type, where this quantum.
Yeah, well, quantum is just a name. It's just like how called. This algebra just has many names.
No, I mean that it's quantization of something.
Yes, it's a difference. It's like a quantization. It came from sort of quantization of function on torus. Like it's not like I don't know. The word quantum might be misleading here. It's called like this.
All right. So, like Heisenberg algebra also can be thought as a quantum quantization of algebra. Okay. All right. Okay. And since we do not have infinite time, so what's the relation to is there anything else we want to say about moduli of instantons before you explain the relation to integrable systems?
Well, yeah, we need to introduce several notions So some special observables, which then will give us back this spectral curve integral system. Yeah.
Okay. So now, of course, you were interrupted too many times, but how much time do you need?
Wait, let me think. I wasn't thinking about it like that. So basically, the first part was supposed to be 20 minutes, right? So
yeah, I understand, but now having realities of the life in mind, how much time do you want? So we
well, yeah,
start
it
to
depends on how much you
negotiate.
would like to hear, right? Like, I don't know. The thing, I don't even know what the form was 1 hour, right, for your talk, or
Technically, yes, you can go over the time, but kind of for the reasonable amount of time. Like 15 more minutes, will it be okay?
well, we'll get to maybe the spectral curve, but
Because
yeah,
you already speak, of course, with a lot of interruption. You speak for 1 hour, and in Kansas, people probably need to go to lecture, so we do not have infinite.
yeah, I understand. So I don't want to hold anyone. So yeah, even 50 minutes we need to stop. I will stop whenever we
Yeah, but
go,
then
basically.
having this in mind, you maybe get
Compress
down to
something.
some conceptual things which you wanted to
Yeah,
say.
right. But if it would become to compare the stock, most likely the only thing which I would throw out is the introduction, right? I can't really.
Yes.
It's pretty dense already. It's like I just giving bare minimum of definitions to get to the point, basically. Yeah,
Okay.
except for the introduction, right? Which is like motivation, which I think is also very important because otherwise it's not clear what the problem is solving. Nikita's motivation basically to solve the quantum separation of variable for Calogero-Moser system in this form which is predicted by Sklenin. But we're not quite there yet. But we made several important steps, so to say. Which was
But what's the relation of that story to moduli space of instantons? Where is an integrable system? What does it mean?
yeah, okay. So let me continue. I think I'll get to it soon. So basically, we need to introduce some observables which will play the key role in this relation. So because M and K is the moduli space, it has it has a universal sheaf, and it has this projections. We could construct a class in this K-theory of M like this. We will take first pullback of skyscraper sheaf of 0 on this P2, then we tensor it with its universal sheaf, and then we push forward into M and K, and then we need to take this batch sum again. So yeah, probably this is also like ill-motivated mathematically, but physically Nikita was considering it because it just related to spectral determinant of the scalar field in this gauge theory. So he was hoping that it should make some sense. Yeah, and indeed it was like pretty useful. So if the first observation that if we take the expectation value of y of x, it will has poles in x, and if we want to get the relation to the spectral curve, which was just a polynomial spectral curve equation with a polynomial of degree n in x. We want to something without poles first, and Nikita was able to find some sort of new observable, which is built of bunch of y's in such a way that its expectation value has no poles in the finite region of x, which is called QQ character. It starts approximately like this. So it starts with y. Epsilon this epsilon 1 plus epsilon 2. And then it adds additional terms. So for finite m, there is actually infinite number of terms. So the idea was that he has that this y of x, poles coming from here cancel out with poles coming from here, but this numerator produces additional poles, each one, and they need to cancel as well. So we will need to add additional 2 terms, and so this term will grow like this. Here's also additional matrix or function here. They will keep growing, and eventually be some sort of sum over Young diagrams. This expression.
Will it be infinite sum?
Yes, in this case, it's an infinite sum over Young diagrams. Okay. Yeah, and so basically, this means that this thing, depending on the setup which we're working in beta equals 0, so cohomology case, it's a polynomial of degree n in x in beta non-equal to 0, so equivariant criterion. It's a polynomial in exponent minus beta x, degree n, and in this mysterious equivariant elliptic cohomology, it's a theta function in exponent minus beta x of degree n. So, and indeed, there were some papers where Nikita checked that the coefficients of this polynomial, they are related to conserved quantities in some way, which I'll maybe explain later if you get to it. Yeah, but now if you want to get a spectral curve, it's natural then to consider the following expression. Yeah, basically Nikita just guessed it. Let me write it. E x. Yeah, here also there is a big step. Yeah, if we, I don't know, if somebody already heard anything about Nikita's talk, to get to Nikita's research, to get the classical integrable system, classical spectral curve, we need to consider the limit epsilon 1, epsilon 2 goes to 0. So in this, I will just define this as a limit. And so for the same for y of x. Yeah, and the relation to the spectral curve is then, well, we could check how this equation transforms and under the shift of z, and we'll see that it's almost periodic. So the hypothetical relation would be that gamma of xz is equal to r of xz divided by theta function. Yeah, and you might ask in what sense it's a relation, because our r of xz is expressed in terms of these variables a1, an, right? The coefficients inside of it, which are equivariant parameters which we have left. And here we had xi, pi. So these ai serve as action variables, actually, something like this. And the proof, it basically it constructs the relation, so to say, inexplicitly between them, through obtaining the lax matrix from this gauge theory.
How do you obtain lax matrix? So far, I see something like a spectral curve only.
Yes, you're right. That's the whole. That actually was the whole point of the story, in some sense. Yeah. Okay. So let's say. So how much time I have left? Yeah.
Maybe 5 more minutes.
Okay. Let me think. I could do.
You can replace part of something by references if there are. Like you can say something which is not in the archive, and for the rest you can.
Yeah, we haven't. Yeah, I see, but we haven't published it, so
You
I
have
can't
not
even.
published this last part, which is on your slide, or what?
Yeah, about which I need to explain about the lax matrix yet. So yeah, okay. But basically the topics which are left unexplained is the quantization. Yeah, there is a natural quantization of this formula. So in this case, to literally look like this. Then I'll just say it very briefly. So if we keep epsilon 1 non-zero, we'll have the formula yeah, the same thing. Big I. Here the big I means just the same thing, the limit of this curly high, but with epsilon 2 goes to 0, epsilon 1 finite. And here the ordering is correct. So basically, the way we know it is because for two reasons. First of all, with this ordering, we have a nice factorization formula, which allows us to prove relation to the classical case and to the lax matrix. Wait, let me write it down. Wait.
Is it a continuation of the formula above, or what?
Yes, this thing is just equal this. This is just equal. You mean, yeah, this is just equal this product. Yes, right, correct. So this is such product. And y of x is also just the limit of curly y of x when epsilon 2 goes to 0. So the ordering is important because otherwise this formula would not hold. And without this formula, we would have no relation in the classical limit to the lax matrix. And the other way that we know it's the right ordering is because we actually found a solution. Um, Basically, Nikita guessed it also as well in a nice form. I probably also will not explain in details already now how it looks like, but it requires this additional more complicated geometry. So the moduli space of instantons, it talks about instantons living on this plane C2 with equivariant parameters epsilon1, epsilon2, right? And when I was talking about QQ character, secretly this insertion of a QQ character, it's a partition function, comes from the integral over the moduli space of U1 instantons, which live on an additional C2 plane with equivariant parameters epsilon3, epsilon4, where epsilon3 is m and epsilon4 is minus epsilon1, minus epsilon2, minus epsilon3.
So what is related, this more complicated geometry is related to what?
Yeah, so basically the statement is there is some sort of moduli space of crossed instantons, which are basically instantons on a cross.
Yeah. And so then, you write down analogs of QQ characters, which you mentioned earlier. What do you get as a result? What you get in the end?
Yeah, basically the thing is the expectation value of he was equal to expectation value of 1 in this crossed instantons. Instantons.
Why do you need cross instantons if you already wrote before some formulas?
Yes.
Just to interpret. Okay.
There is the result for the wave function. Exactly, you're right. Absolutely. Formally, I don't need it. Yeah, I gave you independent definition from pole constellation. But there is a geometric picture behind this pole constellation in some sense.
Something should be compact. Or what?
You're right. The smallest space of crossed instantons is compact, and this X is like one of the equivariant parameters, and that's why it has no poles, and that's how Nikita proved it geometrically. But I will not go into this direction. I'll just want to mention that the solution is also expressed as the partition function of some U1 instantons, but living in this plane C14. So basically, this kind of shared direction.
I'm afraid it's time to kind of, well, if I knew how things will go, I would ask you to start from the end and go back, because this geometry is interesting, I mean, by itself. So you consider some interesting moduli spaces, you define some maybe ill-defined mathematically, maybe not, I'm not sure, generating functions, and then you make a connection to something which we have no idea. This Calogero-Moser, I am sure it makes physicists happy, but not every mathematician. But moduli spaces, it's kind of more geometric object. And basically you consider some kind of equivariant integration and define some spectral curve for the integrable system, if kind of to see it from the cosmos, from the very, very large distance. So that's what's going on.
Yes, basically, yes. We consider some equivariant integrals, and we obtain some things which are important for integral systems, like the spectral curve, the quantum spectral curve, and the solution of this quantum spectral curve. The wave function, the hypothetical wave function in separate variables.
Okay, so Andrei, unfortunately, I think it's time to kind of to somehow to put a point.
Yeah, I know.
Dot
So
50.
basically, you're probably right. Originally, I was thinking about not giving introduction about integrable system.
Yeah,
Then
so
we
your
will,
original thought was, in my
was right.
opinion, was right. Yeah,
Yes,
but
but
anyway, when
I
do
made
you
a mistake.
expect
So yeah,
to put your paper in the archive?
I don't know. It depends on Nikita. Basically, the second part, which exactly actually what I did so far, I only talk about what Nikita did mostly himself, is the orbifolded version.
Okay.
When you replace the moduli space of instanton with affine Laumon space, you probably know it too, right? If
Yeah, I know what the Laumon space is, but I don't know how it is related to all
yeah,
that
so
story, but
everything the same. We do the same thing. We introduce Y functions, QQ characters, and fugacities, and we have all the same things. But everything this equation becomes matrix equation. So Y function become matrices, high become matrices, and fugacities become also n variables, and these fugacities Q1, Qn, they become related to canonical coordinates in Calogero-Moser system and Ruijsennars system. From this matrix factorization equation, we will get the expression for the Lax matrix, and followed instanton, this one for instanton, its fractionalized version will become the Becker-Hazer function. And everything works in such a way that the determinant of this matrix product in the classical limit will become the product in this scalar form. And that's how we know that this spectral curve and its quantization is actually the spectral curve of Calogero-Moser system. Yeah.
okay.
So that's the brief, brief summary in just one.
We'll wait for your paper. All right. So, thank you very much. Are there any questions? Okay. So, if there are no questions, thanks again. And ask Nikita to speed up.
Well, I forgot to answer your question. So basically, Nikita, he found a better proofs of all my theorems, which I was able to prove in this case. So basically, he found nicer version, he finds some kind of general algebraic identity from which both matrix and non-matrix cases follow naturally, and he want to write it in like a nice unified way. So
Okay. So
yeah.
then,
But it takes time. So I'm saying
I see.
I don't know what will happen in the end. Basically, maybe it will be like this paper, or
Hope
maybe
this time will be finite. Yeah, of course.
yeah, I don't know. It's approximately 1 year ago. I did it basically. We still just kind
1
of
year is okay. I have
yeah.
some project which are 15 years kind of still not published. Yeah, all right. So
I
good.
agree with you. Not a big
All
time.
right. So then good luck and thank you for the interesting talk. And please send me your notes, whatever, if you will be able to make a PDF file or something.
Yeah.